So now we move on to one of the main results, perhaps the main result of this chapter on topology of our class. Uh, Let me first give you the setup. I have a function from a metric space to another metric space. I'm going to be talking about open and closed sets here according to the topology given by this metric. Same thing here, I use this metric. And we're going to see that we can reformulate the concept of continuity of F in terms of topology, in terms simply of pure open and closed sets. And okay, so what's the statement? We're going to show that these four conditions over here are equivalent. Let's go through them. So the first one is saying just that f is continuous, right? If I look at a point x here, it's mapped to f of x. Now, condition number one says that if I take a sequence of points that converges to x, the sequence is mapped to something that converges to x as well, to f of x. That's a definition that we saw before, so that's continuity according to the definition we've had so far. Okay, what's condition number two? So let me erase all these dots because I'm going to muddle the picture a little bit. We're going to need the dots later, but anyway, I'm going to draw new dots. So suppose I have a set here F that's closed according to the topology of Y. It's closed according to the metric of Y. What I claim is that its pre-image is also a closed set. And just remind you, the pre-image is the set of all points in the domain of the function such that f of the points lies in the set F that you consider. So these are the points x such that f of x lies in the set F. And I claim that if f is continuous, then the pre-image of any closed set is also a closed set. Now, number three is sort of the same thing with open sets. And let me just remind you, okay, if this is closed, the complement is open. And it's easy to see that the pre-image of A is exactly the complement of this guy. So if this guy is closed, this guy is open, and vice versa. And so 3 and 2 are really equivalent. They're saying that the pre-image of an open set is an open set. It's the same thing as showing that the pre-image of a closed set is a closed set. Now, just to make sure, right? So what I'm saying here is that f minus 1 of f complement, this complement in Y, is the complement of f of the pre-image of f, right? This complement being in X. And this should be clear for the picture, right? All points in X, they either have their image in F or their image in A because F and A are complementary. Okay, so 2 and 3, I'm going to claim that we already kind of argued that they're equivalent. Number 4 is another usual definition of continuity that doesn't use sequences, but rather this epsilon delta notion, right? I give you a point x and a tolerance epsilon, an error tolerance epsilon. You have to find me a delta such that any point that's delta close to x has value of f epsilon close to f of x. So this is another standard definition of continuity. I mean, it's not hard to show that 1 and 4 are equivalent just from first principles, but we're going to do it in this sequence. So I'm going to show that 1 implies 2, 2 and 3 I've argued are equivalent, 3 implies 4, and in the end we're going to show that 4 implies 1. And then we have that all of these things are equivalent, right? Okay, so let's get started. I'm going to start with 1 implies 2. So what is my assumption? My assumption is that, okay, here's F, right? So I'm moving the name of the set outside. And this is F minus 1 of F. What do I know? I know that any sequence here that converges to a point in F. And now I want to prove the same thing here. So I should take a sequence of points that converges and show that its limit belongs to F minus 1 of F. Okay? So assume 1 implies 2. Assume, right? So I wanna prove that F minus 1 of F is closed if F is closed. So I'm gonna show that by the sequence criterion, right? So assume that X sub n is contained in F. X sub n converges to X in the space X. What we want is that X belongs to F, right? We don't know, but we want that. Okay. What do we know, right? So we are assuming 1, remember. Therefore we know that F sub X sub n converges to F of X. And these points, okay, now comes, okay, so this is wrong, right? So let me maybe redo this. I have a sequence of the pre-image, as I wrote over here. I assume that the sequence converges to a point in X. And when I show this point is also in the pre-image of F. So what do I know? I know if this is a convergent sequence, then the values of F along the sequence also converge, right? So they should converge. That's what continuity is about. And this is a sequence of points, and this is the main point. These points all belong to F. And why is that? Well, these are points in the pre-image of F. What does it mean to belong to the pre-image? It means that if your X sub n, and X sub n belongs to the pre-image, well, maybe replace this by X tilde to not mix up that. So X sub n is one of these points whose F belongs to the set F, right? Whose value of the function belongs to the set F. So X sub n is contained in the pre-image means that F of X sub n belongs to F. And we're assuming that F is closed, right? This is for all n. So we have a sequence of points in a closed set that converges. The consequence of all this is that, therefore, F of X must belong to F as well. But what does that mean? It means that X is one of these points such that F of X belongs to F. Therefore, it means that X belongs to pre-image of F. Okay, to say everything again, because I sort of screwed things up in the beginning, I want to prove that the pre-image of a closed set F is closed, right? So I take a sequence of the pre-image that converges, and I want to show that its limit belongs to the pre-image as well. But all I can use are properties of the function and of the set, which I know is closed in Y. What I notice is that when I map this sequence by the function F, this has to be a convergent subsequence because of 1. This convergent subsequence has points inside the set F, which is closed, therefore the limit is also inside F. But if F of X is inside F, it means that X belongs to the pre-image of F. So that does it for 1 implies 2. I've already noted that 2 and 3 are equivalent just because of these issues of taking complements and stuff, right? That's the usual set theoretic shit that we've been doing. Now, I want to prove that 3 implies 4. And it implies, I mean, if, you know, there are many ways to prove that these things are equivalent, but it's sort of odd because in some sense what I'm going to show you is I think it's really the simplest possible way. So let me, just because now I care about A, I have F and A, so this F minus 1 of A. Let me move this outside. This is F minus 1 of F minus 1 of A. And so I want to apply this, so I'm actually going to change the picture a little bit over here. I'm going to prove that 3 implies 4, look, can you tell that I'm talking about an open ball here, right? So I'm looking at, I want F of X prime to belong to the open ball of radius epsilon around F of X. So let me draw this ball over here. So my set A right now is this open ball of radius epsilon around X, right? As I said, I choose epsilon. I choose X, and then we have to find a delta, right? So this is dA, right? I'm going to apply 4 with A equal to ball in the space Y of center f of X and radius epsilon. Open ball. What do we know about this ball? Well, we don't know much. Well, here's one thing we do know. We know that pre-image is an open set. So now X belongs here, right? So, sorry, this is f of X, right? So A is the ball around f of X. So in the pre-image, right? So f of X belongs to A. So X belongs to f minus 1 of A. And let me maybe draw that with this dashed line to just to say that this is an open set. So X is in here. It's an f minus 1 of A. So, so we're taking A like that. And then by 3, since we're assuming 3, this implies that f minus 1 of A is open. And as I noticed, because f of X belongs to A, then X belongs to the pre-image of A. Now we should do what we know how to do by instinct, right? I tell you I have an element in an open set, and you tell me, okay, there's a ball around this guy that's entirely contained in the open set. Sorry, this is not a good drawing, so maybe move the line a little bit here, and now I have a ball. And this is a ball, to emphasize, because I have two metric spaces, this is a ball in the space X with a metric d sub X. Okay, I told you there's something kind of funny about the proof, even almost silly. The point is that we're now done. And we just have to translate what I just wrote over here to what I have over here, right? What does this mean? It means that, okay, there exists a delta. What is this open ball? I mean, it's precisely the set of all points in X whose distance is less than delta to X, right? So I'm saying that any point that belongs to this ball belongs to the pre-image of A. So what does it mean to say, okay, any point that satisfies this belongs to the pre-image? What does that mean? It means that f of X prime belongs to the ball around f of X of radius epsilon in Y with metric d sub Y. But what does that mean? It means that the distance between f of X prime and f of X is less than epsilon. And maybe that's not so easy to see, but I mean, right? So what is my claim? So my claim is that if I take A like this, I look at the pre-image, I find an open ball inside it. Now, this delta, which is the radius of the open ball, is precisely the guy I'm looking for. Again, this is saying that the whole open ball is contained in the pre-image of this guy. That means that any point here is mapped to this ball, right? So it's saying, so any point within distance delta from X is mapped to a point within distance epsilon from f of X. So if I have X prime here, its image must be in the set, so it's f of X prime. And so we're done, right? So basically what I'm saying, okay, is that saying a point belongs to this open ball says it's a distance less than delta from X. Saying that a point is this open ball says it's a distance less than epsilon from f of X. And that's it. Okay, so basically what we're saying, okay, 3 implies 4, and 4 is in some sense a very particular case of that, of 3, because here you say any open set, here I just say, just care about balls. I want to say that the pre-image of a ball contains a ball around X. That's it. Okay, there's one last step missing, which is that 4 implies 1. So let's do that and finish. Or finish with some comments maybe. So if I want to prove that 4 implies 1, I have to take a sequence that convert, okay, sequence X sub n contained in a set X such that X sub n converges to X and X. And I want, let me erase this A, which I don't need anymore. So both 4 and 1, they use the concept of open or closed. They're just statements about metric, the two metrics, right? So convergence in the two metrics. So this is what I want to prove. Good. Okay, how do we do it? So what is the same that what we want is equivalent to saying the following, that for any epsilon there exists an n naught such that for all n greater than n naught, the distance in y between f of x and f of x sub n is less than epsilon, right? Saying that f of x sub n converges to f of x according to the metric ty, which is implicit all the time, is saying that this is true. But here, okay, so this is what we want to show. So given epsilon greater than 0, there exists a delta as in condition 4, right? We're assuming 4. So we know if for any epsilon, if for any x, right, the x is here, I have a delta, right? And we know that x sub n converges to s. So this means that there exists an n naught such that for n greater than n naught, we have that the distance between x sub n and x is less than delta, and so the distance between f of x sub n, f of x is less than epsilon. Let's see if this is clear. All I'm saying is that, okay, so I give you an epsilon, I want to find out the n naught. And I want you to find the n naught. So here's what you can say to me. Okay, for each epsilon, I fix x, I fix epsilon, so there is a delta. So I know that all points within distance delta from x satisfy this condition. Now the point is, because the sequence x sub n converges to x, the points in the sequence satisfy this condition for all large enough n, right? So meaning for all n larger than some n naught, I have the distance from x sub n to x is less than delta. And then, look, I'm applying property 4, right? So if the distance of x sub n to x is less than delta, then the distance of f of x sub n to f of x is less than epsilon. So the question was, how for each epsilon, how do you choose the n naught? The answer is this. For each epsilon, you first find the delta. From delta, you fix an n naught such that for all n greater than or equal to n naught, the distance between x sub n and x is less than delta. And that n naught already is there exactly the guy you need to ensure this. Right. So again, by assuming 4, you know that there is a delta for each epsilon. By assuming that x sub n converges to x, you know there is an n naught such that for all n greater than n naught, distance of x sub n to x is less than delta, and then you're done. And that's it. So now we know that 4 equals 1 implies 1, so these things are all equivalent. To emphasize, right? So 1 and 4 are metric definitions of continuity. As I pointed out in the beginning, it's not really that hard to prove that the two are equivalent. So there's nothing to that. 2 and 3 are purely topological definitions of continuity, meaning that these definitions actually make sense in any topological space. So if you want to talk about continuous functions in a topological space, this is how you, or between topological spaces, this is how you would define things in terms of pre-images of open or closed sets. So that's also not difficult. what is interesting is the relationship between the two, right? So that you have these two things, and somehow I really think that, the most kind of enlightening way of proving that these facts are all true about continuous functions is to do the sequence, because you can see that somehow you move from here to closed sets very naturally. These are very clearly equivalent. This is also very natural, and this last step is also not too hard. It's a little bit harder to go directly from 1 to 4, in my opinion. But in any case, this is kind of a second glimpse of this world of topological properties, right? So topological properties, they make sense on their own. And even when you have a metric, it might be useful or convenient for some purposes to think of things in terms of topology. And we're going to be doing that for the next sections of the course. Before we move on to other subjects, mostly compact sets and connected sets, we're gonna stop a little bit and talk about induced topology. And the main point is this. So here I told you what a continuous function is if the domain of the function is x. What if the domain of the function is a subset of x, right? That's something we consider in our definitions. And induced topology is going to help us deal with that. Thank you.